I think we should review PX phase diagrams before we get to TX phase diagrams. So I have this Excel tool that I've made, and it's again, it's a pressure composition. Let me see. Pressure composition phase diagram. And so what that means is we're plotting the pressure of the mixture over the composition of the mixture. So the X part is the mole fraction. And so we have two substances here. We have water and methanol. We have water's boiling point and methanol's boiling point, both in Kelvin. And we have the vaporization of water. So that's the amount of heat it takes to vaporize a mole of water. And this is the amount of heat it takes to vaporize a mole of methanol. They're pretty comparable because of the hydrogen bonding. So most of the organic substances have a much lower heat of vaporization because the intermolecular attractions are smaller. And so it doesn't take as much heat to evaporate a mole of, say hexane than as it does to a mole of water. Because water, you got to pull apart all those hydrogen bonds. And then we have the temperature of the system that we're talking about at this point. So then we can calculate those pure vapor pressures using the Henderson-Hasselbalch equation. No, I'm sorry, the Clausius-Clapeyron equation. Too many equations. Okay, and so then once we have those pure vapor pressures, then we can start plotting things. So we can plot Raoult's law and Henry's law. So let's see, how do I want to do this? Let me adjust this to where it goes to 0.2. Okay, there we go. So on the x-axis, we have the mole fraction of A. And so we look up here and we see that solvent A is water. So pure water vapor pressure is right here. And that makes sense because water has a higher boiling point, so it has a lower vapor pressure. Does that make sense to everybody? Yeah. So this is the vapor pressure of pure water. And over here is the vapor pressure of pure methanol. And so on the x-axis, we have that mole fraction of water in ethanol. So at 0% water, we have 100% methanol. And so what I want to point out here is that from that pure vapor pressure to 0, that's Raoult's law. So the arrow, can you see the arrow? Yeah, the arrow is pointing at Raoult's law for water. It's just a linear function from 0 pressure of water all the way up to its maximum pressure of water. And so this straight line here is Raoult's law for methanol. From 0 pressure from methanol when there's 0 methanol in the system, linear trend all the way up to its maximum vapor pressure for methanol when it's 100% methanol. And then this black line right here is the total vapor pressure. So both of those added together. So if you're at a 50-50 mix or a 60, here, let's go to the 60-40 mix. So you've got 60% of the pure vapor pressure of water plus 40% of the pure vapor pressure of methanol added together to get the total. So this would be an ideal mixture would be these straight lines, the Raoult's law for both substances and then the Dalton's law, which is the sum of all of those. Okay. Then we have the actual behavior shown with these curved lines. So the curved lines show the actual vapor pressure of water and methanol. And you see when you add a little bit of water in methanol, the water vapor pressure is shown as being higher. So it would rather evaporate than to be stuck in the methanol. And the same here over here, this is the methanol line. Again, a little bit of methanol in water is going to be very present in the vapor phase. It's going to have a higher vapor pressure if these actual lines are correct. And notice this dashed line. Notice where it comes from. So this dashed line is the Henry's law for water. All of the water stuff is blue. So for this dilute water, you put a little bit of water in a lot of methanol, and this is the Henry's law vapor pressure for water. Now notice the actual is this curved line. So where does Henry's law actually apply? It applies at very dilute solutions of water. And Raoult's law applies to very concentrated solutions of water. And the same with the methanol. Raoult's law matches the experimental data when methanol is very concentrated, and Henry's law matches the data when methanol is very dilute. So you just need to get that in your head. Henry's law is for dilute solutions. So you can write that down. That's a safe thing to remember. Henry's law is for dilute solutions. And Raoult's law is for the concentrated solutions. And these curved lines in the middle, we used Margulies' equation, which we're not really going to discuss in this course. I've mentioned it, but we're just going to stop at Raoult's and Henry's laws. So that's the PX phase diagram: pressure on the y-axis and composition on the x-axis. Are there any questions? Notice you can obviously do this in Excel. I put all of these formulas in Excel and plotted them. The interesting piece is the Margulies equation, but you take my master's class, the graduate level class, you'll actually create this tool yourself. I might put it online just to have you guys, if you want to play with it, that'd be fun. So now let's go into the TX phase diagram. So now we're going to have temperature on the y-axis. And so this is comparing the two. Notice over here on the PX phase diagram on the left, the pressure versus mole fraction. And we have this region here where there's two phases in equilibrium. If you're at high pressure, then you have the liquid phase. And if you're at low pressure, you have the vapor phase. And notice when we flip to TX phase diagrams, those two things change places. So look where the liquid and vapor phases are in both of these. Notice in the temperature, the vapor's on top and the liquid's on bottom. And that makes sense. If you raise the temperature, you're going to boil the substance, it's going to be all vapor. But on the pressure side, people mess that up. If you're really at high pressure, you've pushed everything into the liquid state. If you're really at low pressure, you're going to evaporate everything into the vapor state. So vapor state is below the TX diagrams, below the PX lines in the PX phase diagram, and the liquid phase is on top. Okay. And notice also that in this case, the X and the Y are not the same. So this is the vapor phase composition, as you can see from the red line. The vapor phase is red. So let's say we're at 298 Kelvin and 1 atmosphere. Okay, then right here, this is going to be the composition, the boiling point, or it's going to boil here. This will be the temperature, the boiling temperature of this liquid composition. And this, when it's boiling, is going to be the vapor phase composition. So it's high, it's enhanced in the low boiler. So if you're looking at this is the mole fraction of A. So this is the boiling point of A, and this is the boiling point of pure B. So notice how in all cases, the vapor phase is enriched in the lower boiling point. This is the basis of distillation. So if you boil a mixture, the lower boiler is enhanced in the vapor phase. And that makes sense. So let's talk about distillation terminology. So this is a fractional distillation setup. And I took a picture with this infrared camera that I have. It was made for it's kind of a sad thing. I spent like $200 on this camera to take infrared pictures, and it attached to a phone. It was really cool. It turned your phone into being able to take infrared pictures. Yeah, but when you have something that attaches to the phone, be careful. Don't make the mistake that I made. It's going to be tied to that phone model. So I bought this years ago with an iPhone 5. Well, that's not supported anymore. So that investment is pretty worthless. I was able to generate some great images for a couple of years, and then the updates were no longer supported. And yeah, so if you're going to buy a piece of equipment, a piece of instrumentation, beware of tying it to a phone. Okay, especially when it like has to fit on the phone. Like it was like a case. You put the phone in, and then it turned it into an infrared camera. So it's no longer supported, and it's really kind of sad. I can't take pictures with it anymore. But I did get this really cool picture of this distillation apparatus. And so up there at the top where you have the thermometer, that's the condensate temperature. That's the lowest boiling substance in the mixture. It's condensing at the top. This is going to be collected in this condenser here. So you know this is the condenser, the water jacket. And then the fractioning column is in the middle. And the reason it's got a kind of a different shading right here is because there's a jacket around this too that we don't have any water in. It's just a long piece of glassware. It could function as a condenser too, but we're just using that as a fractioning column. But that's what this orange thing is, kind of an artifact of having an extra layer of glass around it. Okay, and then down at the bottom is the still bottom, also called the pot. Okay, and then that's the pot boiling temperature. So there's a temperature gradient from hot to cold. So the pot boiling temperature is going to be, let's say, if you have a TX phase diagram, like we showed just in the previous slide, and you've got a mixture right here. That temperature right here is the pot temperature. Okay, and this temperature right here is T condensate. Which is up here. So those are the terms that I'll be using in talking about fractional distillation. And this is how they show up on a TX phase diagram. So when you boil this substance, okay, this mixture of liquids, the vapor is highly enriched in substance A. Okay, substance A is the lowest boiling point. And what happens? Well, it flows up the column a little bit as vapor, and the temperature is dropping as it goes up because there's a temperature gradient. So it gets cooler as it goes up. So what's going to happen is that it's going to eventually hit the walls where the temperature is this temperature right here. Notice that's a lot cooler temperature. So it's going to condense right there at that temperature. That is the temperature at which this vapor would condense. If I'm above that temperature, the vapor doesn't condense. So it bounces around that column, and it's still gas phase, but it's hitting the walls, and it's changing its temperature as it hits the walls. So it leaves the surface of the solution, and it's banging into the walls. The walls are still hot, so it doesn't condense. Eventually, it hits the wall where it's cool enough to condense, and it sticks. And then other molecules stick, and it forms a droplet. Makes sense, right? The temperature's dropping and it starts to condense at a certain layer. And you'll actually see this if you start a distillation and you watch carefully. You'll see the condensation line, and it'll move up the tube, and then it reaches the top and it starts to drip into the condensation flask. So you'll actually see this line around the fractioning column work its way up all the way to the top as the thing warms up and gets its temperature gradient established. Okay, so when it hits this, it starts to roll down the side of the fractioning column, right? And what's happening when it's rolling down the side of the fractioning column? It's getting hotter. So it boils again. It drops maybe a millimeter or so, and then it starts to boil again. And so when it boils, guess what? That solution is really enriched in A, because now it's this droplet that's boiling. And then it moves further up the condensing column until it gets to a point where it's much cooler, and then it condenses again. And so it condenses at this temperature, which is even further up the column. And then finally it condenses at the condensate temperature, and it stays there until all of the A is removed from the mixture. So that's what these zigzag lines are doing right here. So in these two different distillations, you can have a huge separation between the vapor phase and the liquid phase, or maybe if the molecules are more similar, you can have a more narrow two-phase region. And this is what we would say, these compounds are harder to separate. 5 theoretical plates are needed, more difficult to separate. Easy. Do y'all remember, how many of y'all have had instrumental analysis? Have y'all had that already? Okay. Do you remember in talking in chromatography, they were talking about how many theoretical plates were needed to separate 2 compounds? It was in chromatography, and it was, again, the stationary phase and the vapor phase for separations. Some of these gas chromatographs, the 30-meter columns, think about how long that column is, 30 meters, okay? They have like 15,000 theoretical plates. So you can separate things like butane and isobutane. Same molecule, essentially, just you've moved the carbon instead of being at the end to the middle of the molecule, and now you've got isobutane. Same mass, pretty close to the same boiling point. It would be impossible to separate those two compounds from each other using fractional distillation. Okay, but in gas chromatography, you could use the same theory as you have for fractional distillation in chromatography, and you could figure out how many of these recondensations you would need to separate butane from isobutane. And it would be in the thousands of theoretical plates. Okay, so chromatography, it's easy to get that kind of separation, thousands of theoretical plates. But notice how much you can actually put through there. Your sample sizes have to be incredibly small, and you have to have a super sensitive detector. So distillation is useful if you want a large volume. You want to separate large volumes of substances. Chromatography is useful if you want to separate minuscule volumes of substances. Prep column chromatography, where you're trying to separate large volumes using chromatography, it's incredibly tedious. You got to pour tons and tons of eluent through, and it's not a very efficient process. But for minuscule sample sizes, chromatography is way better than distillation in terms of separating compounds. But if you need a bulk amount, if you need to separate a large amount of substance, then distillation is the way to go. But the substances have to be fairly different from each other. Okay. So this is what's going on here. Let's just show it once again, that this temperature here is, we start at this mixture here, X, now we're talking about XB. Okay, so we're starting here, start. So we go up here, we heat the pot, so this is in the pot. So this XB here is in the pot. It boils at this temperature, which is down here. Then this piece right here is in the fractioning column. These are all the recondensations and reboilings. This is happening in this area here. And does that make sense conceptually? As it goes up, it cools, and then it condenses, and it re-evaporates, and condenses, and re-evaporates, and condenses all the way up until at the condensation temperature here, for the lowest boiling substance, the T boiling for B, is up here at the top. And then this B, of course, the gas molecules are bouncing all around in here. They get over here where they hit this cool jacket, this condenser, and they condense. And now there's no temperature gradient over here. It's just cold. And so you can collect that substance B over here after it hits that cold water jacket. So that's how we separate liquids. So the theoretical plate, when I was in instrumental analysis, I remember asking the professor, what is a theoretical plate? And he said, well, it refers to bubble plates. He said, but they're not used anymore. And that showed his blind spot. He had never really been off campus, right? It just a professor his whole life, and he didn't realize that when he said we don't use bubble plates anymore, he was being incredibly uninformed, I should say. Yeah, we don't use them anymore in academic circles, right? We don't in chemistry. We put glass beads or stainless steel chain in our fractioning column. We don't have bubble plates in our fractioning column. You could make ancient times, I guess hundreds of years ago or 100 years ago, they made bubble plate fractioning columns out of glass. Yes, it's difficult to blow the glass in that way, but they're no longer used in laboratory separations, okay? But this is what a bubble plate looks like. But they are still used in refineries. So refineries bubble plates are still used there, and they're actually now having a comeback in people who want to make their own spirits, like they want to make their own vodka or make their own, different kinds of distilled spirits. Okay, you can buy brass bubble plates, and so here's an example of one of those for distilled spirits. This is what a bubble plate looks like. So this is the weir. It's called a weir. It's a condensate return, and these are the bubble caps. And the example over here on the left is shown for like refinery. So down here is the crude oil, and you're boiling the crude oil or heating it up. The vapor is going to be enriched in the lowest boiling substances. Okay, this totally makes sense. So the vapor is going to come up here, and it's going to condense, and it's going to fill this bubble plate tray here. Okay, and there's actually a weir right here. I'm gonna draw this with a little wall here. That's called a weir. Think of it as like a little waterfall. So it's a wall that that the liquid can flow over. So it fills up to the top of the weir, and then it drips over that. It's an overflow wall. So if a lot of those vapors fill up this area, then they can overflow and flow back down to the crude oil, and then they can boil again and come back up. Now, we want the good mixing of the vapors with the liquid on that level. And so that's why we have this bubble plate. Notice that the level of the weir is higher than these little exits. So the vapor that's coming up of the high boiler is going to come out these little exits and bubble up through the solution. That's why these are called bubble cap plates or bubble plates. So the vapor has to come up. It has to rise through here. It's going to bubble up through this liquid and interact. And if it can condense, it'll stay in the liquid. If it's still got a lower boiling point, it's going to stay in the vapor. And so it's going to go up and continue higher. And so if it's a low boiler, it'll continue up here where it'll bubble into this area. And if it's, got the boiling point of that layer, then it'll stay. If it's got a lower boiling point, it'll leave and go up. And it'll just keep going up until it finds a layer at which it can condense. And so we have down here, we have crude oil with a really high boiling point. Then we have kerosene with a lower boiling point than crude oil. And then we have gasoline with an even lower boiling point than kerosene. Kerosene and diesel are pretty similar to each other, so we can just say diesel. So this is how we separate crude oil into kerosene and diesel and gasoline and even more volatile substances like white gas, which is even more volatile than just regular gasoline. Coleman fuel, you might have heard of Coleman fuel. It's white gasoline, they call it. And so then we just have these taps here where we can pull off the excess liquid. So that's a bubble plate. And this is what those columns look like in a refinery. So if you get, there's a picture of a refinery here, and this is a fractioning column right here. How do you know it's a fractioning column? Well, it's standing upright. It's actually rusty down at the bottom. That's where the heat is. The heat increases the speed of oxidation. You have bubble plate sections in here, and then you have these taps that come off. So there's taps that come off at different levels. And so like this, let's pretend this is a crude oil fractioning column, and this is the diesel tap, and so that diesel boiling point is producing this liquid, and it's just coming off in a continuous process. You keep flowing the diesel in, you keep pulling the, you flow in the crude oil, you pull out the diesel. Okay. So that's our fractioning column. These are maintenance and sampling platforms, and you have a fraction tap. So this is a simplified drawing of a refinery's most important products. So put in the crude oil and you distill it, and here's all the different things that come out. So some of the vapors are very volatile. You have liquid petroleum gas. So some of these things are residual butanes and propanes. Butane lighters, that's where this comes from, propane for your propane tanks. Then you have gasoline. This is the, well, I don't know which one is more high dollar, but I'd say all four of these are where the money is. And then you have this low-grade fuel right here. Cheap and dirty. Okay. And then asphalt base, that's the tar that goes on our asphalt. And so here we have a situation where maybe we could take some of this cheap and dirty fuel and turn it into the high dollar fuel. And this is where the chemist comes in. I mean, most of this is pretty straightforward engineering. You just build a column with a bunch of mechanical pipes and things, the bubble plates, and it produces these fractions. And the fractions are useful for different kinds of motors, diesel motors, gasoline motors, propane stoves and lighters and stuff like that. But if we could turn the cheap and dirty fuel into clean, expensive gasoline, that'd be worth a lot of money. And so that's where the inorganic catalysis comes in. So Wilkinson, he was an inorganic chemist, and came up with Wilkinson's catalyst to take double bonds and hydrogenate them. So a lot of this cheap and dirty fuel is cheap and dirty because it's got a lot of double bonds and aromatics and so on. So if you could hydrogenate those, then you could create a lighter fuel, something with a lower boiling point and something that would come out in the gasoline fraction. And he changed the percentage of the gasoline produced by the refinery process by just a few percent. It was worth billions of dollars. So Wilkinson's catalyst, he won a Nobel Prize for that. And that's what we're talking about, these cracking units and alkylation units. So these are catalytic units using inorganic catalysts. And so that's where a chemist would come into a refinery area to manage the catalytic processes. And you would need to know something about the chemistry of the oil that's coming in, the chemistry of the catalyst, and the temperature and pressure relationships related to those catalytic processes. Okay. And a lot of times a chemist, so this is the joke, okay? So a chemical engineer needs to know, let me see if I can think of it. 4 things, okay? They need to know what happens when the pressure changes. So this system is under pressure. They need to know what happens when the temperature changes. They need to know what happens when the catalyst is performing well or poorly. And they need to know the number of a good chemist. So and that's from a chemical engineer. So he was joking about his own group. Like, they know engineering well, but they sometimes have a difficult time with the chemistry. A chemist knows chemistry well, but has no idea about the engineering, and so they make a good team. So that's our fractioning towers that we see at the refineries. Now let's look at, before we go on, this is just simple distillation. Let's take the catalysis and set it aside. This is just simple distillation. So this is also why you can't really give someone a molecular formula for gasoline. So when we did our QSPR lab, we just said, okay, hexane is gasoline. And it's a main component of gasoline, but we have a huge number of compounds and that come off at that temperature range. So each one of those bubble plates has a range of temperatures of boiling points in it. And so gasoline is a very complicated substance because it's what we call, it's just a tap. It's just a fractioning tap off of a fractioning column. It's not a pure substance. Okay. And the same with the diesel fuel or motor oil or any of these things. They're really complex mixtures. I mean, hundreds of compounds are coming off at that fraction. Now, some of those compounds are more volatile than others. Some of those compounds will evaporate better in the summer than in the winter. And so the EPA, at least in the United States, has a particular blend for summer, which is a little less volatile because the temperature is higher, so it'll still work in the engines. And then a blend for winter, when it's cooler, it's less volatile and it won't work as well in the engine. So they need a little more volatile mix in the winter. And so they actually fine-tune this process temperature-wise for the summer blends and for the winter blends. Let's look at some not so simple TX phase diagrams. So distillation is supposed to separate the most volatile compound from the mixture, but some phase diagrams have maxima or minima, so they're not ideal. The composition of the mixture at the maximum or the minimum is called an azeotrope. So zeotropic behavior is a normal behavior, so this is azeotropic behavior, so non-zeotropic behavior. And so notice that this blue line is the vapor composition, the black line is the boiling temperature of the liquid, and notice there's this little pinch here. So YA equals XA. Oh goodness, so that's the definition of an azeotrope when YA equals XA. So you see the blue line and the black line touch at that composition. So that's the azeotropic composition. It's the solution whose liquid and vapor compositions are the same. That's a problem if you're trying to separate this mixture, right? Because it's going to go all the way up to the condensate temperature and come out as a mixture, okay? Or it's going to stay in the pot as that mixture. So we'll have to figure out which one is which. So let's take this substance here, or let's start at this point here. So if we start here with this mixture and we boil it, what happens at this point? The vapor is enriched in substance A, because this is the boiling point of substance A. I'll say TB with a capital A superscript, okay? And this is the boiling point of substance B for substance B, okay? So since A has a lower boiling point, the vapor is enriched in A. It goes up the fractioning column and it condenses. And then that drop on the fractioning column starts to roll down. It gets hot again and it re-evaporates. And when it re-evaporates, the vapor has this composition of A. So eventually some pure A comes out into the collection flask. Well, what happens to the pot? So this is what happens to the liquid layer in the pot. It moves left because I've lost some of the more volatile compound. So if I remove A, it becomes enriched in B and it moves left. Okay. If it moves left, the boiling point increases. So the pot's boiling point will increase because I'm losing the lower boiler. So the pot's boiling point is slowly increasing until it hits this point, and it will sit there and stay at that maximum boiling point, and we won't be able to separate all of that A out. So when we have this composition here, then this is going to boil and recondense and boil and recondense and stay that azeotropic composition all the way up to the top of the fractioning column, and it will eventually start to come over as an azeotrope. So the point is, when you have an azeotrope, you can't completely separate the compounds. You can separate one of the excess compounds, but you can't completely separate A from B when you have an azeotrope. So azeotropes are the enemy of fractional distillation. I don't know if you came across that in organic or if they talked about it in organic, but typically when you're talking about distillation, you're going to talk about azeotropes too, and say when you have an azeotrope, you can't completely separate the substances. So there's two types of azeotropes. There's a high boiler, and you can see over here on the left, this is what we have. That the T for the azeotrope is higher than TB for substance B and TB for substance A. So this is the boiling point of the azeotrope up here, so TB. So the lowercase b, the subscript B is just for boiling. So the boiling temperature for the azeotrope, boiling temperature for B, and the boiling temperature for A. So this is a high boiler. Down on this, the one on the right, this is the boiling point for B. Up here is the boiling point for A. And then this, down here, the lowest one, is the boiling point for the azeotrope. So in this particular case, let's start here at A1. Let's put this in the pot. So we've got something that's almost pure A1. It's almost pure A. We put it in the mixture and put that mixture in the pot. So let's say it's 90% A and 10% B. And we put that in the pot. What were we typically trying to do in this case? Well, we would be trying to boil the B off. Right? So we want to purify A and collect whatever B is in there. B is the lower boiling point, so we put it in the mixture. We put that mixture in the pot. It's 90% A, 10% B. Heat it up. We might be a little surprised or concerned that it heats up so high, but again, it's 90% A, so it goes up to this point here and it boils. And then the vapor is enriched in B. That's no surprise. It recondenses in the fractioning column, re-evaporates, recondenses, and then we notice that the thermometer at the top is not reading the boiling point of B, it's reading some boiling point that's lower. And that's surprising, okay? We would expect B to come off, but it doesn't. Some lower temperature shows up, and when we analyze that condensate, we see that it's about 50-50 A and B. So the azeotrope came over, not B. So that's a problem, right? If you wanted to try to separate B from A, you've got 10% B contaminating your A, you want to distill that out. And you look and your condensate is 50-50, not even 90-10. That's weird, isn't it? You have 10% B contaminating your A, you distill it, and you get a condensate that's 50-50. because the azeotrope is a low boiler. So whatever the lowest boiling substance is in your mixture, depending on which side of the azeotrope you are in, if you have a high boiler. But anyway, the lowest boiling substance is going to come out in the condensate. So if the azeotrope is the low boiling substance, then this is collected in the collection flask. Okay. In the condensate collection flask. And then, depending on which side of you're in, the pot is going to move towards pure A. So we're going to lose that excess B, and so the pot will move towards pure A, but it's going to be pure A plus whatever non-volatile residue you have in the still bottom. Okay, and then over here on this side, if we were to boil this, the condensate collection flask would collect pure A if we started here, and then the high boiling azeotrope would be in the pot. If we started on this side, let's say we started over here and boiled it, then because we have more B than the azeotrope, we're going to collect a little bit of pure B out of the collection flask, and then the pot's going to move towards the azeotrope because we're pulling off the excess B. So do you see, no matter which side of this point you're on, the pot is always going to move towards the azeotrope. You'll understand the two things. You've got the collection flask and the pot. Pot will always go towards the higher boiling side, and the collection flask will always be the lowest boiling piece. Okay. And you can kind of treat this like two phase diagrams. So like this right here, it breaks the phase diagram. And if I'm on this side, what shows up in the collection flask is the low boiler, pure B. And what shows up in the pot is the azeotrope. If I'm on this side over here, then the pot still ends up being the azeotrope, but then pure A comes out in the condensate, in the collection flask. Okay, let's look at this one. Let's split this one in two at the azeotrope. If I'm on this side, okay, the pot is uphill, and the pot will be the pure A plus non-volatile residue and junk in the pot. And then the collection flask will collect the azeotrope. And if I'm over on this side, if I start on this side, then the collection flask will again be the low boiling azeotrope, and the pot will move towards pure B. So it's the same as we had for zeotropic phase diagrams, but it's just split in two on either side of the azeotrope. Okay. So let me just sit here and make sure that you guys understand that. So, because this is what I'm going to ask you. If I come into an exam and I say, okay, I'm going to drop you right here on this phase diagram. I'm going to say start right there and tell me, first of all, I might ask you a question, what's the boiling temperature of this solution? Okay, and we got all these different temperatures up there. You might have to estimate the boiling temperature of the solution, right? So this right here would be the boiling temperature of the solution. This is the boiling temperature of pure B, boiling temperature of the azeotrope, etc. But if you start at 1, and I ask you what's collected in the collection flask, and you have several options. You have pure A, pure B, high boiling azeotrope, low boiling azeotrope. Those are your 4 options. Okay. If you start here, pure B is going to be collected in the collection flask. And then the second question will be, what are you going to have in the pot? The high boiling azeotrope will be in the pot. If you started over here, and I ask you the same question, I can say, what's the boiling point of that mixture? You come across here and estimate that number right there. And I say, what's collected in the collection flask? You do the zigzag thing. This is the collection flask. You get the low boiling azeotrope. What stays in the pot? Well, you move yourself up the black line, and whatever the highest boiling point on that black line is, that's going to be in the pot. Doesn't matter where I drop you into this diagram, you should be able to follow those things. If you start over here, let's start right here like we did in the beginning. We come up here, we do the zigzag thing, that's the collection flask. So zigzag downhill, pure A in the collection flask. The pot moves uphill on the black line, and you have the high boiling azeotrope in the pot. So that's a pretty complicated phase diagram, but the principles of interpreting it are pretty easy. And we're out of time. But anyway, I think we covered these pretty well. And so we'll see you next time.